Okay. So, phase 1 and phase 2. Phase 1, transformation. Phase 2 is conjugation. The lab of our body is our liver, you see, and we are able to eliminate these transformed compounds mainly by urine.
Just a question.
Yeah.
The phase 2 is to increase the hydrophobicity of the compound.
Yeah, by put together a residue of a very polar compound. It is a derivative of glucose. And so you see it's a sugar, we'll see hydrophilic. So it is not a chemical transformation, it's not a chemical reaction, it's just a fusion of two different entities, okay? So, every type of compound that we introduce in our body should be eliminated. Okay, nice. We can defend ourselves, yes. But where is eliminated? By urine, yes. And the urine, you know, go to the flow, they reach the river. And then they reach the sea. And so, you see in the picture, fish are inside this big mix of different drugs. And we'll see that a lot of drugs are excreted unmodified. This means that we can take an antipsychotic, for example, and we eliminate this molecule unmodified in the water. And so this molecule can work in the water, and so fish are not depressed. Huh?
But this means that we ingest.
This means that all molecules go into the rivers, yes. And sometimes these molecules remain unmodified and remain still active.
And if we eat that fish?
But, right. But now we see all the different sources of drugs in the rivers. Manufacturing, okay, we know, but perhaps a company can adopt specific filters to block the residue, the elimination of the residues, okay. Illegal drug manufacturing, no filters in this case, I think. I don't know, but pesticides, agriculture, storage treatment, okay. But the problem are residential, but hospitals. We are at home. We use a lot of antibiotics. Perhaps there is a pandemic, I don't know, an infection, a general infection. And so we'll see a lot of tons of these compounds go directly to the river. We'll see now. Okay. So you see, drugs administered to patients, drug residues excreted in urine or feces, a lot of these compounds are resistant to the wastewater treatment plant. They remain unmodified. So we can have purified water containing active drugs, river and lake pollution. In the other case, you see sludge. The sludge contains drugs. Okay, this derives from the agriculture. The general use of drugs in agriculture, but we see only our all aspects related to the drugs elimination, not agriculture in this case, not. Here you have an old table, 2001. Quantity of prescriptions. First position, amoxicillin. Amoxicillin is an old antibiotic, but now it's the most sold antibiotic. It still remains a common antibiotic used in the different therapy. You see, in 1 year, 209 tons in Italy. Tons. You have an idea of 1 ton of powder, of compounds, and 209 tons, it's a mountain. 60% of these 209 tons are excreted still active. So about 110 tons, 20 tons, 120 tons remain active. They go to the river, they go to the sea. So we go to the beach. So you see the predicted environmental loads, 125 tons. You see there are other examples, but the most common is amoxicillin. I like to show these slides just to have an idea about the problems related to the use of drugs. Here you can see how a plant can modify the structure of these compounds. There are a lot of different treatments. Mainly, they use oxidative reactions. They oxidize these chemicals. Peracetic acid treatment, you see UV treatment, oxygenated water and ozone. These are the main treatments used normally in the water plant. Amoxicillin is removed 30 to 60%. But a lot of amoxicillin remain active. In this case, in this class of compound, you see the removal rate is 0. This means that this type of plants are not able to change the chemical structure of carbamazepine, clarithromycin, erythromycin, estrone, lincomycin, spiramycin, and so on. Okay. they remain unmodified. So they go to the river, they go to the sea, and so on. There is a very recent study. You see pharmaceutical pollution of the world's rivers. These scientists analyze a lot of river, and they try to detect what kind of drugs are present in these rivers. You see the sites in the world, so USA, South America, Africa, Asia, Europe, Russia, and so on. Also Australia, yes. And they found, you see, paracetamol, caffeine, metformin, okay. And this is the detection frequency. Because now we have very sensitive equipment. And so it's possible to detect femtomolar, picomolar, very low quantity of drugs. So you see the picture. This is a fish formed by different tablets. So the problem is high quantities, tones, heterogeneous group of substances, different drugs, continuous pollution. They remain active, so biological active substances, a complex mixtures, potential toxic effects even at low concentration. There is a database called, you see, Farms, UBA, where you can see the residues of pharmaceutical in the environment measured in 75 countries. Germany, European Union, worldwide, and so on. It is in Italian, but in Italy they found 596 drugs. Painkiller, antibiotics, antidepressants, contraceptives, and so on. The problem is, normally drugs should be active at low concentration, because it's impossible to take 1 kilogram of drug every day, you know. And so if a drug remains active at low concentration, it remains active also in the river at low concentration. Drugs should be selective to avoid side effects. Drugs should be potent, to take only a few milligrams every day.
Final question, maybe so stupid, but for example, if a fish ingests an active contraceptive.
You see, yeah, I show you. I show you the final result. Yes. The hidden cost of flexible fertility. More than 100 million women use use oral contraceptives, they are excreted in modified with activity at low concentration, and the result is interference with endocrine systems intersex. So we have fish, no male and no more female. This is the final result. And so immature eggs in the tests of male fish, which reduce their reproductive success. Fish becoming transgender from contraceptive pill chemicals being flushed down household drains. This is the final result. The problem is with the contraceptives, yes, but the problem is also with cocaine. In the Po River, around Milan, it's an area of severe use of cocaine. And so you see the problem with the fish. Just a little bit schizophrenic. Illegal drug residues in the water could be affecting native fish. There is another interesting consequence. We know the amount of cocaine in Milan by checking the residue in the Po River water. And so we can estimate about how many million people take cocaine during the weekend. And it is interesting because the same concentrations were found in Sardinia in August. So the people from Milan go to the north part of Sardinia, they use cocaine there, so we know exactly. It's strange. But there are a lot of papers about this topic. It's possible to determine how many people use cocaine by analyzing the Po River water. Yeah. Have you any questions? It's quite interesting. But really the problem is related to the big quantities of drugs excreted by our kidneys. This is the problem. Because, okay, I can collect the expired drugs separately, okay. But in this case, we have, okay, you take antibiotics, please, I collect your urine in this bottle, okay. And then you are taking an antipsychotic, okay, I collect your urine in another. During my life, 30 years ago, I have to take a drug against thyroid to destroy every kind of cells of thyroid because I had a cancer in that time. And it was a radioactive compound. And so they collected my urine because, you know, I was radioactive in that time. And I had to stay alone at home without my children, without my wife, anybody. Because I was radioactive in that time for 1 month. And so I have to collect my urine because I was radioactive. And so to avoid the contamination of the environment. It was quite strange. However, we are here with you and so Okay, questions, comments at home? No? Oh. Okay, we introduce now the metabolism and then we stop for 15 minutes. So, oh, it's in Italian. Okay, phase, it's phase. You know. Phase 0 is the distribution of the drug inside the body. Okay. Phase 1 is transformation. Phase 2 is conjugation. Phase 3 is excretion. You see a pill, a drug, introduced in our body. Oxidation, transformation, phase 1. You can see the metabolites here. Or conjugation, with the, we'll see glucuronic acid is very hydrophilic compound. And so we put together our drug with this hydrophilic compound. We have a stable adduct, you see, and we can eliminate this adduct very easily. Once again, phase 1, transformation. Phase 2, conjugation. These two phases can overlap. Several metabolic mechanisms are simultaneously active on a molecule. So a molecule can be attacked from different enzymes simultaneously, and so can be transformed, conjugate all together in order to maximize its elimination. Here you can see a very simple example of transformation. Barbiton, you already know this type of compound is a barbiturate. It's a very lipophilic compound, can reach CNS very easily, can cross BBB very easily, any problem. And you can see how our metabolism is able to introduce an alcoholic OH function. A very simple reaction of oxidation. Oxidation of the last methyl group of the chain. Okay, it's a short chain, 2 carbon atoms. But on the last, you can see a simple oxidation of the carbon atom, of the last carbon atom, no, the last methyl group. This simple introduction of an OH is able to stop, to transform this barbiton in an inactive metabolite. So no more activity. And this is the first result. And the second result is that we have a more hydrophilic compound that can be eliminated very easily. So the metabolism is able to transform a drug, yes, but it is also able to block its biological activity. It is enough a small change in the chemical structure to finish, to block the biological activity. Very little differences are enough. These are the rules. and you know there are exceptions to the rules. We can have metabolic inactivation, yes. We have seen barbiturates are transformed, and the final result is that we have no more active compounds. Okay. In other case, our metabolism can be able to activate some inactive compounds. So our biological transformation are able to activate exogenous compounds. Or, as smart strategy, we can use metabolic activation to increase the distribution, the CNS, the CNS activity by endogenous activation. In this case, when we have an inactive drug and our enzymes are able to activate this drug after its assumption, we say that we have a prodrug. Prodrug is an inactive drug which can be activated by our metabolism, by our metabolic reaction. So we can manage an inactive drug, or in other case, this compound can be activated, for example, only by insects and not by our metabolism. And only after the assumption of this compound inside our body, our enzymes activate this drug. This is, in the picture, is the most famous example of prodrug. Red prontosil, you see here, red. This compound is colored, is a dye, wool dye. When you make a pullover for your friend and so on, you use this type of dye. Red prontosil is inactive. But if we assume this type of compound, our metabolism is able to hydrolyze this double bond, you see, this double bond between the two nitrogen atoms, and we get this sulfanilamide. Sulfanilamide was the first antibacterial agent discovered about in 35, before the Second World War. Sulfanilamide is active. Red prontosil is inactive. But sulfanilamide derived from an enzymatic hydrolysis of red prontosil. If red prontosil remain in this, with this formula, it's inactive. They should be activated to sulfanilamide to have the active drug. We'll see this These drugs, it's a very old class of drugs, still used in agriculture as antibacterial. We'll see. Okay. Any questions at the moment? Okay, we can stop for 15 minutes, and then I take a coffee. I open the window. Have you any questions at all? Sorry? No? Okay. We can stop for 15 minutes and then we start again 3.5. Okay? Wake up. We start. Allora. Okay. So, we have seen the metabolic inactivation, but also metabolic activation. Another example is phenylbutazone. You see, is a very old anti-inflammatory drug. You can see the introduction, the simple introduction of an IgG group in the carbon chain is enough to block the activity of this compound. There is another metabolite. In this case, you see the OH is introduced on the aromatic ring. And in this case, we get an active metabolite. The metabolite is still active. And so we can have some metabolites, some inactive metabolites, but also we can get some active metabolites. When we have to prepare the folder for the health agency, we have to know every metabolite in the urine. So it is important to isolate and to know the chemical structures of all metabolites of a novel drug, a new drug. So it is necessary to investigate all type of metabolites in urine, in feces. It is requested. Once again, you can see an example of metabolic activation, parathion. is widely used in agriculture, is inactive. You see, there is this sulfur atom. If the sulfur atom is replaced by an oxygen, by enzymatic reaction, we get a paraoxon, very toxic. And these reactions normally is present inside the insects. Where this reaction take place? Inside the plasma, there are a lot of enzymes in the cytoplasm, in the mitochondria, in the lipophilic membranes of endoplasmic reticulum, microsomes. And the main metabolic reaction are reaction of phase 1. In particular, oxidation are the most common reactions, reduction and hydrolysis. These reactions are catalyzed by enzymes, of course. They are mixed oxidases. They are able to introduce mainly hydroxyl groups. And this type of enzymes belong to the family of cytochromes P450. You see the mechanism of action of this type of cytochromes. It is necessary the presence of oxygen, of course, iron, formation of free radicals, you see. It's a metabolic reaction, and normally during this type of reaction there is the formation of free radicals. The cofactors, you have already seen this type of cofactors in biochemistry. So I am not interested in the chemical structure of these cofactors. It's just to remember you the chemical structure of cofactor, which are very important for the enzymes. If we want to inactivate the activity of particular enzymes, we can block the cofactors with particular drugs. We'll see. And so, if we change the chemical structure of some cofactors, we can block the activity of particular enzymes. Okay, you see some substrates for cytochrome 2A6. You see a lot of drugs. In another table with another subfamily of cytochromes. In general, we can say that all drugs are substrates for cytochrome. When we take a drug, this drug can be modified by cytochrome? Yes. In this way, the cytochromes are busy in this type of reaction, and so perhaps they are not able to metabolize other drugs, other substances, because they are already busy with a specific drug. In this case, we say that a specific pathway is blocked, and we can have side effects with other drugs that are not changed, are not metabolized. This is the problem related when we take different drugs together. We can have blood protein displacement, if you remember, in the blood. But we can have also problem related to the different pathways of cytochromes blocked by specific drugs. In fact, if you see on the drug paper, sometimes you can see this drug cannot be associated with this other type of drugs because the cytochrome 2A6 is already occupied and so on. It's very common. Here you have an example with a very, very simple drug called aspirin. Aspirin is an ester, you see, OCOCH3 here, the acetyl ester. Phase 1, oxidation, hydroxylation, dealkylation, deamination, hydrolysis. These are all reactions of phase 1. The main metabolite is the salicylic acid. You see, we can see that this compound is hydrolyzed to get salicylic acid. Phase 1. Phase 2, conjugation. You see, this residue is called glucuronic acid. It derives from glucose, and you know that sugar is very hydrophilic because there are a lot of OH group on this structure, and so the presence of these residues is able to increase the hydrophilicity of this glucuronide, so we can eliminate very easily this aromatic, this benzoic acids residue. So, first 1, hydrolysis. Phase 2, conjugation. Yes, please.
In this case, there is activation or inactivation?
Inactivation. Yes, salicylic acid is it's still an anti-inflammatory drug, but aspirin is more potent. We'll see the mechanism of aspirin. Is able to block a specific enzyme called cyclooxygenase covalently. In the other case, salicylic acid is not able to give this stable block of the enzyme. In this case, we have an inactivation of the drug, yes. It's not so common to find an activation of a drug by metabolism. It's not so common. The examples are very, very few. And so normally you have an inactivation of the drug. Phase 1 reactions. The main family of the phase 1 reaction is oxidations, are the oxidation reaction. Aliphatic carbon oxidations. So if you have, we'll see, if you have an aliphatic chain, you can have the oxidation of specific carbon atoms. Carbon oxidation of alkenes. Aromatic carbon atom oxidations. Nitrogen oxidation. Sulfur oxidations. Nitrogen dealkylations. If we have a nitrogen atom with different substituents, it's possible to have a dealkylation, the loss of an alkyl group. Oxygen dealkylation, and finally deaminations. it's possible to have the loss of a nitrogen atom, a minic group. Phase 1 reactions, oxidation. In particular, we'll see the aliphatic carbon atom oxidation. This means that we'll have an introduction of an alcoholic group, OH group, on the aliphatic chain. In particular positions, not in the whole chain. In particular, in omega position, omega is the last letter of the Greek alphabet. This means that we'll have the OH introduction in the last carbon atom of the aliphatic chain. So if we have, you see, a long chain, carbon atom chain, only on the last carbon atom you will have the introduction of an OH group. Only in the last position, or in omega minus 1, penultimate position. Our enzymes are able to introduce an OH group on an aliphatic chain only in the last carbon atom, or we say in omega minus 1. Because probably the cavity of the enzymes is not so big. It's not able to work to accept all the carbon atom chain if the chain is too long. If the aliphatic chain is located on aromatic ring, so you have a benzene with an aliphatic chain, you can have the introduction of the OH group on the carbon atom very close to the aromatic ring. Alpha position with respect to the aromatic ring. So the OH group can be introduced in the last carbon atom of the chain, in the omega minus 1 carbon atom, and in the carbon atom very close, attached to the aromatic ring. These are the three positions where the OH can be introduced by metabolic reactions. So at the beginning, you can have the simple introduction of an OH group, and in this case you have an alcohol. Normally, this alcohol can be oxidized to aldehyde, and finally another additional oxidation to carboxylic acid. Bless you. Oh. In German we say Gesundheit, and because sometimes I think in German and in English, and so I have to choose the right language. Yeah.
These are the same steps in the detoxification from alcohol.
Sorry?
These last two steps are the same ones involved in the detoxification from alcohol.
Yes, but normally at the beginning there is the introduction of OH, and then a further oxidation to aldehyde, and then to carboxylic acid.
But they are catalyzed by the same enzyme.
Yeah. Okay. It's a lot of oxidative enzymes are present in the liver. And so normally the starting point is an alcoholic group introduction and then a further oxidation in order to increase the elimination of the compounds.
Yes, but for example, when you obtain the alcohol and we have to go to aldehyde, the enzyme
is another family, okay, but is always in the same pathway. Yeah. Aldehyde are not so stable. Normally they are very easily oxidized to carboxylic acids. Another point is that aldehydes can be toxic because they can interact with the amino group of DNA. We'll see during the anti-cancer, in the anti-cancer chapter. And so aldehydes are toxic, normally because they can react with the nucleophilic groups present in the cell. And so the cell tries to transform the aldehyde group in carboxylic acids. So here you can see the oxidation of an aliphatic chain. You see the introduction of the OH group in omega -1 or in omega, the last. And then once again, you can see the example with the pentobarbital. It's a sedative and hypnotic. You see the introduction of the OH group on the omega -1 position. Once again, it's another example, the introduction of the OH group on this methyl group here. Methyl group is located on a benzenic ring, and so if you can see the introduction of the OH in this position. Alkene, double bond, you remember from the organic chemistry, you have a double bond between the two carbon atoms. In this case, you can see that the cytochrome are able to introduce an oxygen atom on the double bond. And we get an oxyrenic group, oxyrenic cycle. Epoxide. Epoxide are very reactive. They can be attached by a nucleophilic group. So an epoxide is very electrophilic, can be attached by nucleophilic groups. Yes. In this case, you see what happens on this double bond of the carbamazepine. You see the double bond formation of the oxyrenic ring, and then the water is able to open the ring, and we have a diol. You see a double alcohol function. You see the 2OH, because there is the intervention of an hydrogen, a water molecule able to open the oxyrenic ring.
To get what?
To get a diol, you see the 2OH group. You have a double alcohol, is a diol. In this case, you have more hydrophilic compounds, so this compound can be excreted very easily. This diol, you see, diol, 2 OH groups. Here you can see what happens to the benzene ring. The benzene ring, there are a lot of double bonds, you know the chemical structure, you know the electrons clouds and so on. We can have the formation of the oxyrenic ring, oxidation. And so we have an epoxide. Epoxides are very reactive. In this case, you see the products, a phenol, is one of the products, and the other one is a another type of diol, two OH groups on the aromatic ring. So in this case, we can eliminate benzene from our body because we are able to introduce hydrophilic groups and to increase the hydrophilicity of this compound, because normally this compound is very lipophilic, you see. Only double bonds, only carbon atoms. It's very lipophilic, the benzene. Here you have an example with amphetamine. Amphetamine are a CNS stimulant, very potent. And to increase the elimination of this compound, our metabolism is able to introduce an OH group on the benzene ring. What happens when we introduce a lot of benzene inside our body? Normally, benzene alone is not toxic. But this compound becomes toxic after metabolization. The introduction of an oxyranic ring epoxide on the benzene structure increased its toxicity. Why? Because we have a very electrophilic compound. You know the cycle, three atoms cycle is very constrained, is very reactive, can be attacked by nucleophiles. And in the cells, there are a lot of nucleophiles. For example, the amino group of the DNA bases. So the transformation of benzene in an epoxide can produce a toxic compound inside the cells able to change the chemical structure of DNA. But fortunately, in the cells, we can find some protective agents, some nucleophilic agents, able to react with these electrophiles compounds, with these electrophilic compounds. You see, this GSH is glutathione. Glutathione is a strong nucleophile able to attack the oxyranic ring and to reduce the tension of the cycle and to block the reactivity of the epoxide. But during the time, the quantity of GSH can finish. And so in that case, DNA can be hit by these very reactive compounds. And so glutathione, will see its chemical structure, is a very potent nucleophile can protect our cells from these metabolites, from these reactive metabolites. Here you can see some procarcinogens. Procarcinogens means that these compounds are transformed in carcinogens compounds by our metabolism. You see a lot of compounds, benzene, styrene, vinyl bromide, benzopyrene. So a lot of pollutants present normally in the environment can be transformed in carcinogenic compounds by our enzymes. So it is another type of activation. In this case, we have the activation of inert species to carcinogens. Here you have an example with benzopyrene. Benzopyrene is present in the cigarette. And you can see what happens in our liver. There is a epoxide formation, you see here, the epoxide group. And in this case, we have a diol epoxide, very reactive, and be attacked by a nucleophilic compound. It is a human carcinogen according to the International Agency for Research on Cancer. Here you have some example of metabolites isolated in the urine and in the backbone, in the structure of the drug, you can find the glutathione, for example, in this case. Here you can see the chemical structure of glutathione. It's formed by 3 amino acids, but the active group is this sulfur SH, you see the thiol group, because at the physiological pH, the SH can lose a proton, and so we have a S minus. S minus is a very strong nucleophile that can interact with the epoxide, with a lot of electrophilic compounds, can protect our cells from the reactivity of these electrophilic compounds. In fact, you can find on the web, where you want, that glutathione is considered a superfood. The teeny molecule with an enormous job. In Germany, glutathione is sold as an anti-diabetic compound because it can protect our pancreas, the pancreas cells, and it's used for this treatment. It's the master of antioxidants, you see. The antioxidant miracle. It's very common also in cosmetic compounds. It can defend our skin from the pollutants, from external pollutants, and so on. Summary of this type of reaction. Oxidation, introduction of an alcoholic group, further oxidation to aldehyde, and then to carboxylic acid, oxidation of methyl terminal groups, you see. once again. In this case, we have the introduction of alcoholic group in the omega -1, you see, and then oxidation. In this case, we get a ketone, no more an aldehyde, because you see we have two substituents around the carbonyl group. Here you can see what happens to this cycle. You can see the introduction of an OH group on a cycloid killer ring. Once again, some example of the oxidation of this methyl group on an aromatic ring. The introduction of an OH in this position. And so here you can see what happens on a double bond with the formation of the oxyranic, the epoxide, and the intervention of water to open this cycle, three atoms cycle. And we get a diol, you see, 2 OH group. We have seen the oxidation of carbon atoms. It is also possible to see the oxidation of nitrogen atoms. N, where N means nitrogen, oxidation. This type of reactions occurs on primary, secondary, tertiary nitrogen atom. And also in this case, we get more hydrophilic metabolites. The goal is always the same, to have a more hydrophilic compounds which can be easily eliminated. You see an amine here, the nitrogen atom can be oxidized. You see the introduction of an OH group, you get an hydroxylamine. We can have an N oxide or an oxime. You see the double bond between the carbon and the nitrogen atom. Or we can have an imine. This is an example, an amine here, and then oxidation and N oxide. N oxide is a dative bond. You see, oxygen is negative charged, nitrogen is positive charged, because we have the donor of electrons to oxygen. After that, after the oxidation, here, for example, you see the carbon oxidation, we can have the loss of the substituents on the nitrogen atom. You see here the ketone and the secondary amine. We started from a tertiary amine and we arrived to a secondary amine with a ketone. There are specific enzymes called monoamino oxidases, MAO. They are able to hydrolyze, to oxidize the bond between a carbon atom and a nitrogen atom. You see, in this case, we have an amine. Monoamino oxidases are able to oxidize the carbon atom in position alpha to amino group, and then we get an aldehyde and then a carboxylic acid. These enzymes are very common in the synaptic cleft. They can act on adrenaline, noradrenaline, dopamine, and so monoamino oxidases are able to block the activity of most neurotransmitters present in the synaptic cleft. In fact, we'll see specific inhibitors of this family, which are antipsychotic. They are able to increase the concentration of particular amine neurotransmitter inside the synaptic cleft. We'll see during the course. Here you have an example with noradrenaline. You can see the chemical structures, 2 OH groups on the benzene ring, 1 OH on the chain, very close to the amino group. Monoamine oxidase, you see, are able to oxidize the carbon atom. No more amine function, so this species is inactive. And from aldehyde we can go to carboxylic acid. Some examples of these metabolites found in urines of patients. Desipramine is an antidepressant. Desipramine is able to block the absorption of neurotransmitter inside the synaptic cleft.
Can you repeat?
Yes, we'll see later this particular chapter about antidepressant. And this family, desipramine, in this case, desipramine is able to block the reabsorption of neurotransmitter inside the synaptic cleft. We'll see. In this case, you can see the metabolization of this compound by the introduction of an OH group directly on the nitrogen atom. A second example is the chlorpromazine. This is an antipsychotic, very potent. It's able to block the schizophrenic people. Chlorpromazine is metabolized on the nitrogen atom. You see the N, the nitrogen oxide. In this case, chlorpromazine is no more active. So a simple oxidation of the nitrogen atom is able to block the potent activity of the chlorpromazine. So here we are, a summary about the reaction of nitrogen atoms. You see that tertiary amines can be oxidized to N oxide. A secondary amines, you see, secondary amines can be introduced on OH group. Once again, at the primary aliphatic, you can see the introduction of OH group and then the dehydration of the compounds, and you get the double bond between the carbon and the nitrogen atom. Once again, introduction of another OH, further oxidation to nitro group. Amines, once again, introduction of an OH group, formation of an N oxide, nitro group. Also on the pyridine ring, this is pyridine, N oxidation, nitrogen oxidation. Also in this case, you have a tertiary amine, then you can get the oxidation of the nitrogen atom. Once again, introduction of an alcoholic group. So here you can see what our enzymes are able, how our enzymes are able to transform all basic compounds, mainly by oxidation, by introduction of an oxygen on the nitrogen group. Sulfur oxidation. Sulfur is a very common atom in the different classes of drugs. You can see that sulfide can be oxidized to sulfoxide and then to sulfone. Sulfoxide, one oxygen atom is introduced, and the sulfone, two atoms are introduced on this sulfur atom. Here you can see an example. Thioridazine is an antipsychotic drug. There is a sulfur atom in this position, can be oxidized, sulfoxide, and then further oxidized to sulfone. You see the oxidation of sulfur atom. So we have a thiol. Thiol normally, in the presence of oxygen, can get disulfide. You see RSSR. Thiol can give a methyl sulfide, which can be oxidized to sulfoxide and then to sulfone. In this case, we can have the desulfurization with the loss of sulfur atom and the replacement of the sulfur atom with oxygen. Nitrogen dealkylation. A lot of drugs have a nitrogen atom in their structure. Normally, nitrogen group, the nitrogen atom has a lot of substituents. So we can have secondary amine, tertiary amine. In this case, you can see what happens on a secondary amine. You see here the introduction of an OH group, and then we have a carbonyl amine, and then the loss of the methyl group, and then we have a primary amine with the formic aldehyde. So it is possible, our metabolism is able to transform tertiary amine to secondary amine and then into the primary amine. An example, caffeine. We know these substances. It's very common. Caffeine is metabolized in theobromine, in paraxanthine, and in theophylline. And in particular, you see this methyl group can be lost. In this example, in this case, we have a theophylline. This is another case, theobromine. Our enzymes are able to take away this second nitrogen atom. In this case, we have a theobromine. Theobromine is still active, theophylline is still active, but just to show you how the cytochrome work. Another example of nitrogen demethylation. This is benzylamphetamine. It's very lipophilic. It's very potent. Can reach very easily our CNS. In this case, you can see what happens on these two carbon atoms, very close to the nitrogen atom. You can have oxidation, and then the hydrolysis of the bond between the nitrogen and carbon atom. In the other case, we have an oxidation of the other carbon atom, and then, once again, the hydrolysis of the bond between nitrogen and carbon atom. We have seen the nitrogen dealkylation. There is also oxygen dealkylation. We have here an example, the methylic ether, the addition of OH group on the carbon atom. Hemiacetal is not stable, and we get a final alcohol with formic aldehyde. It's the same reaction that we have already seen on the amines. Here you have an important example. Phenacetin was an old analgesic drug, painkiller. You see that phenacetin is an ether. You see the oxygen atom in this case has this ethyl chain on your left, and the benzene group, substituted benzene group on your right. In this case, the enzymes are able to hydrolyze the bond between the carbon atom and oxygen, and we have this aldehyde, acetic aldehyde, and then this phenol called the paracetamol. Paracetamol is very famous. The market name is tachipirina in Italy. And paracetamol is very potent. In the past, in the hospital, they used the phenacetin, but after the isolation of paracetamol inside the urine and the investigation about this compound, the scientists demonstrated the strong activity of paracetamol as an analgesic, and so they decide to produce and to administrate directly paracetamol instead of phenacetin. So paracetamol became, in that time, the most important compound against fever, against pain, and today we use this compound. This compound is very common. Here you have another example. One of the chapter that will be treated is related to morphine. Morphine is an alkaloid from opium, from Papaverum somniferum, and the morphine is very potent as painkiller. But there is a synthetic compound called dextromethorphan, you see here, dextromethorphan, which is used as an antitussive in over-the-counter. You can buy this compound freely in pharmacy. Why? Because dextromethorphan is the image of of codeine, is a derivative of codeine. And dextromethorphan is not active in the CNS, is active only as antitussive and no central activity. In this case, please, you can see this ether group, or methyl. You see there is a methyl group on oxygen. And our metabolism is able to dealkylate the oxygen and to give the free phenolic group on the aromatic ring. Dextrorphan is isolated in the urine. Summary once again. Oxidation of nitrogen group, oxidation of oxygen atom, oxidation of sulfur atom, once again, and then you can have free aldehyde with an amine, an alcohol, or a thiol. Deaminations, yeah, okay. 5 minutes and then we can stop. Deamination is the same reaction that we have already seen, because we have already seen that amine group are able to lose substituents. In this case, we have, from another point of view, we are on the carbon atom and we can lose the basic group. It's the same reaction. Here you can see once again the amphetamine, the amine group. The bonds can be broken. The bond between the nitrogen atom and carbon atom can be broken, and we get a ketone and the salts of the amine. So we have seen all reactions. We have seen the enzymes that are able to oxidize the different atoms. Sometimes reductions can be performed. Normally, the most common reactions are related to oxidative reaction. But sometimes we can observe a reduction of the different groups. In this case, we have a ketone that can be reduced to alcohol, to an alcohol. It's not so common. But however, an alcohol is more hydrophilic than a ketone. So also in this case, we can increase the hydrophilicity of the molecule. Here you can see an example with norgestrel. Is an important contraceptive. You see here the ketone function here, and the ketone function can be reduced to an alcoholic function by a reductase. A reduction of nitro groups. Nitro groups are not so common on the drugs because they are toxic. They can be reduced to amino groups, and normally the nitro groups is on an aromatic rings, and so we get aromatic amines, aromatic amines. amines is American, amines is English. However, we can say both of these words. So we get aromatic amines, which are toxic because they are able to interact with the DNA. So the nitro groups are not so common on the drugs. However, you have here an example of nitrofurantoin. It's a very old antibacterial. You see a nitro group in this point, which can be reduced to aminofurantoin still active. But really, there are not so many examples of this compound, of this group. Reduction of azo groups, double bond between two nitrogen atoms. You see, you can have the reduction of this double bond, and we get two different amines. The example we have already seen just before. Prontosil, rosso, red prontosil can be reduced, you see here the double bond, and we get the sulfanilamide, the active drug. Okay, just a moment. Okay. The last reduction of disulfide. Disulfide can be reduced to thiols. This is the last example. No drugs with these groups are present, so just to say that it's possible the reduction of disulfide to thiols. Okay. So for today, I think we can stop here. Have you any questions about the metabolism? Tomorrow we can start from the hydrolysis because we have some important example of prodrugs to explain. And then we have other part, important part, chemical transformation. But I want to have time to explain this part.
All of those reactions were phase 1 reactions.
Please,
all of those reactions that made were phase 1 reactions.
Yes, phase 1, yes. Okay. Tomorrow we will explain phase 2.
Okay.
Yes, only phase 1. Only transformation. We have to, I want to explain the hydrolysis, but it's I need time because I have a lot of example of prodrugs. So it's important. So have you any question at home? Everything is okay? Okay, no questions? Okay. Okay, perfect. Okay, have you a nice evening, dear students. And then we see tomorrow morning, 10 o'clock, we start, okay? Tomorrow, dear students, we start at 10 o'clock, tomorrow morning. Arrivederci, ciao.